All right. Hi, everyone. Paul here. And I'll actually give you the next three lectures, including this one. So this lecture, I'm going to be talking about deep generative models. And for the next two lectures, next Tuesday and next Thursday, I'll be talking about reinforcement learning and some ways of optimizing for discrete outputs. And then we're going to kind of revisit these deep generative models next Thursday so that we can actually study deep generative models for generating text. So today is mostly going to be on deep generative models for generating continuous outputs. So today we're going to talk about deep generative models, and I think there's a bunch of people doing really good work on deep generative models. I think I'm using some of the material taught at CMU's PGM class and also Stanford's deep generative models class. So today is just going to be a really brief introduction, and if you really want to know more about these deep generative models, you should really look at the PGM class and the deep generative models class for more detail. So let's start. And at any point, just feel free to type in the chat if you have questions, and either me or the other TAs will try to answer these questions as soon as possible. So today we're going to cover three things. We're going to start by introducing these generative models and describe how different they are from your discriminative models, your supervised learning methods that most of you have seen so far. And we're going to start with some basic generative models, and we're also going to go into a class of two very popular generative models. These are called variational autoencoders and generative adversarial networks. We're going to go into some detail, and these are some really powerful generative models because they leverage both the strengths of these graphical models, which give you structure and modeling your data, and at the same time, they also combine it with these flexible and scalable inference that you get when you use like these deep learning and neural networks. So these have been very popular and used a lot in generating images, in generating text, and in generating all sorts of multimodal data. So we're going to go into in-depth explanation of both variational autoencoders and generative adversarial networks. So starting off with generative models. So generative models, usually you're given data, just X. You're not given labels X and Y. So you're just given some text, some images, videos, or some high-dimensional multimodal data. And the goal here is to model P of X. And this is different from discriminative learning or supervised learning. We're given both data X and labels Y, and you try to estimate Y given X. So that'll be estimating the probability of P of Y given X. So in this case, we just want to model P of X. So what does it mean to model? So there's a couple of things that people usually look at when they're trying to both learn and evaluate these generative models. One thing is that if you learn P of X, if you're given a new X, you should be able to evaluate P of X. So realistic looking data, so usually realistic images, should correspond to a high P of X values. And likewise, images that are not as realistic should correspond to low P of X values. That is more of the evaluation problem. And evaluation is really important because it also allows us to do things like anomaly detection, where you have like some really useful images that look realistic and you want to assign high densities to it. And for anomalies, you want to estimate low densities for it. So that's more of the evaluation problem. Another thing that people usually look at is the sampling problem. So if I learn a P of X, I want to be able to sample new data X according to P of X. So that means regions of high density of P of X, which correspond to realistic looking images, you want to be able to sample them with higher likelihood. And likewise, low regions of P of X, which correspond to unrealistic images, you don't want to sample them as often. So you want to be able to sample these images and sample these texts and therefore be able to generate new data. And in general, this goes for both generative models and also unsupervised learning. The goal is always to do representation learning where you want to learn useful features, right? So if you're looking at these generative models for dog images, you want to be able to define a generative model that lets you sample new dog images, but at the same time, you want to be able to learn features that tell you that dogs have ears, they have tails, they have this particular shape, and so on and so forth. So throughout, like for both VAEs and GANs, not only are they useful for evaluating and sampling new data points, they're also generally very useful for representation learning. So you can take all these latent variables and eventually use it for some task. So these are the main things that people look at when we talk about generative models. Just to go a bit further, in addition to just sampling P of X unconditionally, People also kind of care about sampling according to some content or category C. So you want to build a model and you want to sample P of X given C. So in this case, C can be a category such as faces, outdoor scenes, from which that you want to generate images of. So this is called conditional generation. And a lot of the methods that we look at in this lecture can also be extended to conditional generation. Another thing which people care about is this thing called style transfer. So instead of just generating images from content, you're given both a content or a stylistic change as well as the initial sentence X1 or initial data point X1. So that could look like we're given all these sentences that start from consistently slow. So that describes both content and style. And style is some stylistic change that you want to go from negative to positive. So the goal here is to be able to retain all the content in the initial sentence and just change it according to the style. So you would change consistently slow to consistently good, consistently fast. And likewise for images, you also want to keep the main content. So these are a row of houses. You want to keep the main content, but just change it according to a new style. So this is a style transfer problem. And many of the models that we look at in this lecture can also be extended to take in both C, stylistic attribute, as well as some input data, which you want to keep the content of. So this is a brief introduction to generative models. So how do we actually, what is like the go-to approach most people use when they actually study these generative models? So a lot of people use latent variable models. And what latent variables means is that you're going to start with images X, and these images are high dimensional, and there's a lot of variation in these images due to things like gender, eye color, hair color, pose, and so on. And unless these images are annotated, these factors of variation, such as gender and eye color and hair color, they're not explicitly available to you. So these are what we call latent variables. So latent variables in general are unobserved variables that you would like to explicitly model so that given another set of latent variables, you can generate more data. So what this looks like in a Bayesian network format is that you would have data X, and if you recall for Bayesian networks, LP went over it last lecture, you always have these nodes, and these shaded nodes represents nodes that are observed. So in this case, your data X is observed. And the nodes that are not shaded are those that are hidden or are latent variables, so they're not observed. And these are essentially the ones that you want to learn. And these directed edges basically model this generation process, in this case, going from Z to X. So you model your conditional distribution P of X given Z. So you only have a data set with these shaded variables X that are observed. You have these unobserved latent variables that you would like to correspond to these high-level features, such as gender, eye color, hair color, and pose. So ideally, if you had a lot of domain knowledge about images, about these face images, and you had lots of data, then you could define a generative model exactly. You could define this latent variable model. So you could have some variables like gender. You could have a hierarchy where ethnicity determines both eye color and hair color, and you would have pose. And together, pose, eye and hair color, and gender would generate your image. This would be ideal. But of course, in the real world, you don't have that much domain knowledge. Sometimes it's really difficult to specify all these conditionals by hand. And they're usually unobserved. So usually you're just given a bunch of images without labels for the people's gender and eye color and hair color that are appearing within these images. So then what we can do is that we can learn these latent variables instead. And that is the whole goal of these generative models or latent variable models, which is how can we learn these unobserved latent variables? How can we learn both their values, their distributions, and their structure, only given observed data points? So we all know that neural networks are very powerful. Neural networks are able to learn many nonlinear functions and approximate many complex distributions. So what we can do is that we can just try to learn these using neural networks. So in this case, X, again, they're images, and we're going to assume Z is some continuous latent representation. And since it's continuous, we can put a prior on it. And these priors, we can just choose a Gaussian prior, which is the most standard prior someone would choose for a continuous representation. So given a prior on Z, how can we define this generation process P of X given Z? as given by this directed arrow. Well, we know that neural networks are powerful. So what we can do is that we can define a Gaussian distribution where the mean and variance are nonlinear, highly complex nonlinear functions of Z, as parameterized by mu theta and sigma theta, where theta are your neural network parameters. And by making mu and sigma, deep or convolutional or recurrent, you're able to express many types of structures in real-world data. So if you want to model images, you could start with some simple latent representation and have a bunch of convolutional layers to actually generate the image. And likewise, if you want to model text, you can start with, again, a continuous representation Z, and you could have a sequential autoregressive decoder using recurrent models or transformers to actually model text. So these are really expressive methods. And the hope here is that after training, Z will actually correspond to meaningful factors of variation, these meaningful latent variables. And another good thing that we want is that, given a new image X, we want to be able to encode these features. So we want to be able to do feature extraction, not just generation from Z to X, but also given a new image X, I want to be able to uncover what representation it is so that I can eventually use this representation for a bunch of tasks that I care about. So you might want to model P of Z given X as well. So obviously, using neural networks, they're powerful, they're great, but they're also very hard to solve, and we'll see some of these issues soon. But let's just start simple. Let's start simple, I think, with a simple generative model that everybody knows, just to kind of motivate what these latent variables are. So hopefully everyone has seen a mixture of Gaussians. In a mixture of Gaussians, there's two sets of parameters. So first of all, you're going to start with a latent variable Z, and this Z basically represents which cluster you're in. And you're going to define a categorical distribution over these clusters. And given this particular cluster Z, each of these clusters are parameterized by a single Gaussian with a single mean and a single variance. So each of these clusters look like this. So blue corresponds to a first cluster with mean mu1. You have another cluster in red, another cluster in green. So although each of these Gaussians are very simple, by having a mixture of Gaussians, you're actually able to cover many modes in data, and you're actually getting a pretty expressive model. So what a generative process is that you want to be able to first sample Z, in this case from a categorical distribution, which defines which cluster you're in, and then you want to be able to generate a data point by sampling from that Gaussian. So if you chose your categorical distribution to be this Gaussian, and then you would use the third mean and the third variance to actually sample data from this third Gaussian. And mixtures of Gaussians are actually pretty useful. Given data, you're actually able to fit these latent Gaussians to cover the space and actually learn these clusters such that they group together semantically meaningful parts of the data. And oftentimes, again, in this case, we have a very complex data likelihood, and that's shown in red. And we are actually able to approximate this data likelihood by just 3 Gaussians. So when we're talking about these generative models, what we usually care about is actually being able to measure P of X, both to sample from it and also be able to evaluate it for new data points X, and sometimes also to optimize it so that you can maximize this log likelihood from data. So we know that Gaussian mixtures are really simple, and we can solve them using expectation maximization. And they're also pretty useful in learning these clusters of data. But one issue with these Gaussian mixtures is that they're unable to learn features. So given a new data point X, you're not able to learn what a good representation of this data point is. Because in some sense, this mixture of Gaussians only defines a generative process that goes from your latent variables Z, your mixture of Gaussians, to data, but it doesn't encode, it doesn't have an encoding process that actually takes data and encodes it into this latent representation Z. So Gaussian mixtures actually motivate. VA is actually an extension of these Gaussian mixtures, where instead of defining these the P of X given Z as these simple Gaussians with like a single mean and a single variance, we're actually trying to learn the means and variances of these Gaussian distributions given some latent representation Z. So how do we actually learn these variational autoencoders? So again, we're going to start with a joint distribution P of X and Z. And we're usually given a data set D, where for each data point, we only observe the X variables. If you recall this Bayesian network, X is the shader variable that you observe, and the Z latent variables are ones that you don't observe. So how can we learn what these Z's and what these parameters should be? So as usual, we're going to do a maximum likelihood estimation. We're going to try to maximize P of X for X across the data set, and we're going to take log because taking log allows us to transform this product into a sum over logs. So this is in general any model that you have with some parameters. You're going to try to learn these parameters data such that they best fit the data. That's maximum likelihood estimation. So now you have this term, your summation of your data points, and you're going to take the log likelihood of each data point. And we know that we have this structure as imposed by this graphical model. So we have both X and Z. So how can we bring Z into the picture? Well, what you can do is you're going to take, instead of just modeling P of X, you're going to model a joint distribution between P of X and Z. And to go from a joint back to your X, you're just going to marginalize by summing over Z. That allows you to incorporate both X and Z into the picture. But what we're going to soon realize is that this summation over Z is highly intractable. So if Z was binary with just 30 dimensions, you have to sum over all 2 to the 30 terms of Z taking on each particular configuration. And if Z is continuous, this integral over all possible values of Z is also very difficult, and you're not going to get a closed form solution. So soon you realize that while you want to use neural networks to learn this variational autoencoders, you're going to run into a lot of troubles, especially when you try to model this high-dimensional data with also high-dimensional latent representation Z. So the key here is that we need cheaper approximations to actually be able to optimize for these VAE parameters. So how are we going to do that? So for the next few slides, I'm going to kind of derive the training process, the approximate training process of variational autoencoder. I think variational autoencoders have been here for a long time, but it's still pretty important to know how these things are derived, because these derivation techniques are useful not just for variational autoencoders, but in general useful for many approximate inference methods in complex graphical models. So here's what we can do. So again, we're going to start with a log of your joint. We know that this summation over Z is very difficult to compute. So instead, what we're going to do is we're going to introduce a Q of Z at the top and Q of Z at the bottom. So these will cancel to 1, so I can just multiply this inside. Why is this useful? So by taking summation over Z weighted by Q of Z, that basically converts to an expectation over Z. Expectation over Z of what? What's left over inside is your joint divided by Q of Z. So why do you want to do this? So intuitively, you want to choose Q of Z, which is what we usually call a proposal distribution. You want Q of Z to be simpler. We know that your joint distribution is complex, your P's are complex, but I'm going to choose Q to be a simpler distribution, and allowing me to a simple distribution that actually allows me to sample Z from Q of Z and compute this expectation using multi-color samples. So right now, we're still not there yet. Usually, you want expectation to be right on the outside, right, so that you can actually convert this expectation into an empirical average. But we have a log on the outside. So what can we do? So we're going to use Jensen's inequality. Jensen's inequality basically states that if you have a concave function, which looks like this. So for concave functions, what it means is that if you just take 2 points and draw a line between them, the value of the function lies above that of the line, right? So log is concave because log essentially looks like this without it dropping down. So Jensen's inequality basically states that if you have a concave function, log of the expectation is at least the expectation of the log. So we're going to apply Jensen's inequality here and change our log of the expectation to be at least an expectation over the log. And this is already starting to look better. Why? Because right now we have an expectation on the outside, and we know that if Q of Z is chosen well, with Q of Z is simple to evaluate, I can actually sample Z from Q of Z, evaluate what's on the inside, and then convert my expectation into an empirical average. And we know that if you take enough samples, if you take enough samples, this empirical average will actually be a very good estimate of the true expectation. So this inequality here is called the evidence lower bound. In particular, this term on the right-hand side is called the evidence lower bound. So again, what we started off was we had this data log likelihood, which is what we care about. This is really difficult to compute. And I was able to introduce this proposal distribution Q of Z that allows me to derive this evidence lower bound, which at least we're starting to get an easier way to compute it. And this evidence lower bound actually holds for any probability distribution Q over your latent variables. So this evidence lower bound, we're going to start with your data log likelihood, is at least this amount. If you look at this a bit more, it's actually equal to the expectation over Q log of your joint. I'm going to move this log of Q to the outside minus the entropy of Q. So entropy is a term in information theory that quantifies how much randomness there is in this distribution. So intuitively, if Q of Z was uniform over Z, that would have the highest entropy with the most randomness. Gaussian, because it's peaked at its mean, would have lower entropy as compared to a uniform distribution. And what would have least entropy would be something like a delta distribution that is just deterministic at a single point with probability 1. So you know that this evidence lower bound holds for any probability distribution Q over my latent variables. And equality actually holds if Q of Z is exactly equals to P of Z given X, my posterior. And that makes sense, right? For Jensen's inequality, what we essentially did was that if this concave function was exactly equal to the line, then they'll be equal. This would be equality. And similarly, if Q of Z is exactly equal to your P, you will get equality. You will be able to exactly compute your log likelihood of your data using this term. But of course, in practice, we know that P of Z given X is really difficult to compute. And we want to choose Q of Z to be as close to P of Z given X as possible for being easy to compute. So in practice, we can never hope to have equality and optimize the data log likelihood exactly. But instead, we're going to try to choose Q of Z to make the evidence lower bound, which is a lower bound to your data log likelihood. I want to make this lower bound as tight as possible, so that by maximizing this evidence lower bound, I can also approximately maximize my data log likelihood. So I want to choose Q of Z to be as close to P of Z given X as possible for being easy to compute. So this term is quite vague. What does it mean for a distribution Q to be close to a distribution P? And there are actually methods in statistics that allows us to quantify how close two distributions are to each other. And one thing that is most useful here is this KL divergence. This KL divergence is exactly one type of divergence in a class of many divergences that allows you to estimate the divergence between two distributions. So the KL divergence is given as follows. So the KL divergence between Q and P is given by an expectation over Q, log of Q over P. So this integral over Q, dz is exactly the expectation over Q. And this term inside will be log of Q over P. So first notice that this KL divergence is not symmetric. The KL between Q and P is not the same as the KL between P and Q. So then you might ask, why do we want the KL between Q and P and not the KL between P and Q? Well, again, it goes back to the fact that if you have a KL between Q and P, you can compute it as an expectation over Q and something here. And the expectation over Q is something that we can actually approximate if Q is simple enough by taking samples from Q and taking the empirical average. If I had the KL between P and Q instead, then I'll be taking an expectation over P instead. And P is what we started off with. P is a really difficult data log likelihood function that we do not know how to compute. So by taking KL between Q and P, we are actually able to choose Q to be simple and therefore be able to compute the expectation over Q more realistically. So if we look closer at this KL divergence, just because it's an expectation over Q, let's take a look at what sorts of cases will make this KL large and what sorts will make it small. So we know there's an expectation over Q. So if Q is small, then this first term is going to be low. you're going to be weighting it by a small value of q. And that means you don't really care what the term behind it is. Just because, q is linear, is a linear term, and log of this is going to be a logarithmic term. So as this is small, it doesn't really matter what this is. It's going to be dominated by this small q of z term. So if q is low, then we don't care. So we really care about the cases where q is high. We're taking expectations over regions where q is high. So if q is high, then this is going to be high. And basically, I want to learn. I need this p to be high as well, so that this term is close to 1, and log of 1 is going to be 0. So that would incur a small loss to my KL. On the other hand, if q is high and p is low, we're going to take a large value divided by a really small value. This is going to be huge. And that's when you pay a price. If q is high and p is low, that's when you have to pay a price and incur a large amount of cost in KL. So what it looks like pictorially is, if I have p, again, p is a really complex distribution. It's defined by your data. You might have multiple modes corresponding to high-dimensional images. You can't compute what p is. You're going to define a simpler distribution q. If q is low, so in these regions, q is low, we don't care what p is. And for regions where q is high, I want to make sure that q matches p almost exactly. That's when you can minimize and get a small KL. So note that for this KL divergence to be defined, as you can see here, like the support, which is the values of z over which q and p are defined, the support is really important. And in this case, just because p is on the denominator, wherever q is bigger than 0, it must also be that p is at least 0. Otherwise, you'll be dividing by 0 here. So what a KL would encourage you to do is that, for a very complex multimodal distribution p, I'm going to try to find a q values covers some high areas of p, and it might miss other areas of high p. So that's the KL divergence. So this KL divergence is actually really important in the evidence lower bound, because you can actually rearrange this KL divergence and actually obtain the evidence lower bound exactly, plus the log likelihood of the data. And there's no coincidence here. There's no coincidence why I chose to introduce a KL divergence as a distance between distributions, because that's exactly the term that will appear in deriving these evidence lower bounds. So KL is exactly equal to the evidence lower bound plus the log likelihood of the data. And another property of KL divergence, because it's a distance, that the property is that it's non-negative. So rearranging, we can actually rederive the evidence lower bound just starting from the KL divergence as well. So the log likelihood of the data is again at most, it is at least the expectation over q, log of your joint, plus the entropy of q. And again, equality holds if q equals to p, because the KL between q and p, if q and p are exactly the same, is equal to 0. So the KL is going to be equal to 0 instead of at least 0, which means that the log likelihood of the data is exactly equals to the expectation over q, log of your joint, plus your entropy. And that's not just the best part. The best part is that this KL divergence now exactly gives us a gap. It exactly tells us the gap between this evidence lower bound and the log likelihood of your data. And that allows us to exactly quantify how well our chosen Q distribution is. So the closer our chosen Q is to P, as measured by the KL, the closer our evidence lower bound is to the true likelihood. And again, that reinforces the fact that we want to choose a Q that is as close as P as possible, while making sure that Q is simple enough to sample from, so that you can eventually compute all these expectations over Q. And that is essentially the basis of variational inference. You're starting with this very complex distribution, P of Z given X, as your posterior. And you might have multiple modes, and that's shown in blue. And you're going to define these tractable variational distributions, Q of Z, with some parameters phi. These are your variational parameters. And you want to try to learn these variational parameters such that Q of Z fits this P of Z given X as best as possible. So in this case, let's just assume that P of Z given X is this complex multimodal distribution. You can't even write a closed form for it. You obviously can't sample from it. You can't really compute anything. But what you can do is you can define these variational distributions Q just as simple Gaussians. Simple Gaussians with a parameter for its mean and a parameter for its variance. So in orange here is a Gaussian with parameters mean 2, variance 2, and another Gaussian here with mean -4 and variance 0.75. And the whole goal of variational inference is that you want to optimize these variational parameters phi, so that your Q of z is as close as possible to your P of z given x, while being simple to compute. So in this case, this posterior, your P is better approximated by this orange Gaussian, this orange variational distribution than the green one. So there's going to be a smaller KL between this Q and this P as compared to this Q and this P. That is the whole basis of variational inference. So now we've turned it into an optimization problem where phi is all possible settings of your variational parameters. And for each particular setting of your variational parameters phi, that's going to define your evidence lower bound in red. At the same time, it's also going to define a KL divergence between Q of z as given by your variational parameters and your actual posterior, which is hard to compute. And with respect to phi, the log likelihood of your data is actually constant. So log likelihood of your data depends on theta, but with respect to phi is actually constant. So the goal here is to find a good setting of these variational parameters phi such that the KL divergence between your proposal distribution Q and P is as low as possible, and therefore your evidence lower bound is as tight as possible, is as tight of a lower bound as possible with respect to your data log likelihood. If it's as tight as possible, that means that optimizing this evidence lower bound will give you the best approximation to actually optimizing this data log likelihood. So that is the most important relationship here to derive variational autoencoders, which is that the log likelihood of your data is equal to the evidence lower bound plus the KL between your variational distribution, which is free for you to choose, and the true posterior of the data, which is complex, which you want to approximate. So in practice, you want to be able to learn these variational parameters, as well as the other parameters in your model, including theta and any other parameters in the model jointly. So how can you do that? So we're gonna again go to the evidence lower bound. It's something that we derived. We know that this is easier to compute as compared to the true log likelihood of the data. I'm gonna rewrite this evidence lower bound this way. So again, expectation over Q, log of your joint. And we used to have an entropy term, but the entropy is exactly equal to the expectation over Q log Q. That's the definition of entropy. I'm going to subtract log of P of z, and I'm going to add log of P of z. So recall what z is. If you recall what P of z is, so z is your latent variables that you want to learn in your autoencoder, and P of z is just some prior that you're putting on top of these latent variables. So in the case where z is continuous, you will just put like a Gaussian prior over your z's. So I'm going to subtract log P of z, I'm going to add log P of z. I'm going to group the first two terms together. So this joint minus log of the marginal is going to get log of P of x given z. And the second term, my log P of z minus log Q of z under the expectation of Q is exactly the KL divergence between your Q of z and P of z. So let's look at these two terms more in depth. So the first term is actually a reconstruction term. Why is that? So what this term does is that, let's first look at each of these terms in more detail. So P of x given z essentially takes in z, and I'm going to define some parameters theta. In practice, these are neural network parameters theta. And I'm going to transform z into your data x. This is your generator, the generative model. In autoencoders, that's also kind of known as a decoder that takes z and actually generates a data x. My Q of z given x will take in x and use parameters phi to reconstruct, to actually predict which latent variables correspond to that particular data point. So that is the inference model, or also known as the encoder model in these autoencoders. So what this term looks at in total is that you're going to first take x, you're going to encode it using your inference model, and you're going to do it multiple times so that we can approximate this expectation. And once you have these latent variables z, I'm going to put it through my generative model and try to reconstruct my data x. That is this term. And I want to make sure the reconstruction of my data x is as high as possible with respect to log likelihood. So that is exactly reconstruction. It encourages the predicted values of x to be as similar to as the input values of x as possible. And the second term is actually a prior. So again, this Q function, we're taking your data x and encoding it into a set of latent variables. I want to make sure that the set of latent variables that I'm encoding using my data is as close as possible to my prior over z. And my prior over z is this Gaussian distribution. So it encourages this set of predicted latent variables through the inference model to be as close as possible to the prior. So all these derivations allow us to get the elbow, which we know that is a good approximation for the true data likelihood. And this elbow can actually be decomposed to a reconstruction term through an autoencoder. So first inferring the latent variables from x and generating data from x and making sure that x is of high log likelihood, as well as a prior term, which makes sure that given a bunch of samples x, the latent variables that you encode follow a similar distribution to this prior that you want these latent variables to follow. So that's exactly the autoencoder perspective. This is usually what people just present if they wanted to explain to you variational autoencoders really quickly. But all we did in the last 30 minutes was basically a derivation of why variational autoencoders exhibit a reconstruction loss and this prior loss. So now we know that we have this reconstruction loss and this prior loss that allows us to learn these variational autoencoders. But in practice, because we want to do gradient-based learning and combine it with neural networks, it's actually a trick here. It's not as trivial as it seems to just directly optimize this. So why is that? So we need to compute two sets of gradients. Again, we have two sets of parameters. One is theta, one is phi. So we call here theta is the parameters for the generative model from latent representations to your data, and phi is the inference model from x to your latent variables. So there's two sets of parameters they want to optimize, both theta and phi. So to do that, we want to be able to take gradients of this loss function with respect to theta and phi. So the gradients with respect to theta is easy. Why is that? I can just write it out. A lot of the losses here is the expectation on the Q, log of P of x given Z minus the KL. The KL term does not depend on theta, it only depends on phi, so that goes away. And this term in front here, this expectation is with respect to phi. Again, that doesn't depend on theta, so I can move my theta into the expectation. And this P of x given Z, which is the decoder part of the model that takes Z and outputs x, that is the part that actually depends on theta. So what I can do is that I can replace my expectation over my Qs with just samples from it. So I'm going to take n samples. I'm going to take n samples of these latent variables Z, because this is what latent variable Z with respect to the distribution of your Qs, with the distribution of your latent variables as given by Qs. And for each of these latent variables Z, I'm going to try to use it to predict my data X with using my parameters data. And then I'm going to try to maximize the log likelihood of being able to reconstruct data from these latent variables that came from distribution corresponding to Q. So I can change this expectation over Q using a sample average. So this is easy. Difficult part comes here, where you want to take expectations with respect to phi. So what happens here is that we know that this evidence lower bound actually contains expectations with respect to phi. So you can no longer push the gradient with respect to phi through the expectation and take samples from it, just because this expectation also depends on phi. So what are we going to do here? We're going to use this thing called the reparameterization trick, which is a very common trick. It's very important in these generative models. in this simple setting, again, you want to compute a gradient with respect to phi of some expectation over Q, which depends on phi, and some value R. So you don't really care about what value this is on the inside. So this is equal to an integral over Z, the probability, the Q of Z, which is the probability of Z that depends on phi, and the value of R evaluated as Z, where Z is some continuous variable. So what can we do? So let's just assume, because in our settings, our Q of Z are just Gaussians. Assume that Z is an even simpler Gaussian, a Gaussian with just a mean parameter and a variance parameter. So this Gaussian doesn't even actually depend on your input X. So it's just a fixed, or just two sets of parameters, a mean and a variance. So how can we actually sample Z from this Q of Z so that we can approximate this expectation? So one way of sampling is to just directly define this Gaussian with mean and this variance sigma square and sample this entire vector Z. Another way of doing so is to just sample a single noise vector, so epsilon from a standard Gaussian. And once you have an epsilon from standard Gaussian, you can actually put this epsilon through a linear transformation by multiplying it with sigma and adding mu. And that actually gives you Z with the exact same distribution that you want, just because you have the property of linearity of Gaussians. So that is also an equivalent way of sampling Z that also allows you to sample Z according to this distribution. But instead, you're not sampling Z directly, you're just sampling epsilon from a standard Gaussian. So I'm going to call this linear transformation G. It depends on epsilon and also phi, because in this case, phi is this mean and sigma parameter. So this way of sampling and reparameterizing is actually the key that will allow us to compute these expectations. So normally you have an expectation that requires you to sample Z from Q of Z times R of X. Instead of sampling Z directly, I'm going to replace it with sampling these standard unit Gaussians from standard normals. And once I sample an epsilon, I'm going to apply this epsilon through my linear transformation to actually get the Z vector, which is from the same distribution that I want. And then I'm going to put this Z through whatever R of Z that I care about. And what that looks like is that it'll look like an integral over P of epsilon, because it's sampling these epsilons. And once you have an epsilon, you're going to run it through this linear transformation and actually apply R and the Z that you get from putting it through this linear transformation. So what's the benefit of that? The benefit there is that if you now want to take an expectation with respect to phi, you're going to convert it to an expectation over epsilon, your function inside. And now this expectation over epsilon no longer depends on phi. So you can move your gradient with respect to phi into the expectation.